So the main thing that we need to know about roller coasters in physics is that gravity is pretty much the thing that powers a roller coaster. So engineers, when they design a roller coaster, they think about a lot of things, but one of the main things they think about is gravity. And then what gravity does is it pulls the roller coaster down. This causes an acceleration of the cart. The acceleration of the cart causes a velocity. The velocity is then changed in its direction by the track. And that change in direction is a change in acceleration, which can apply different forces to the roller coaster, and that's what makes the roller coaster fun, is that we feel all these different forces on our body as we change from one direction to the next. And this is all based on Newton's first law of motion. An object in motion will want to stay in motion, and it's in a straight line. So our body wants to go in a straight line, and the cart just kind of jerks us around, and that's how roller coasters are able to do loop-to-loops, is that your body wants to keep going in a straight line. The track forces you to go in another direction. And so what a loop-to-loop does is it redirects your direction so fast that your body doesn't have time to fall. And so anyways, all that stuff's a lot of fun. And so I guess if we're going to talk about roller coaster design and physics, the first thing we should talk about is gravity. And so when we talk about gravity, we have to talk about Sir Isaac Newton. He was the one that discovered gravity when the apple fell on his head. The only problem is he didn't really understand how it worked, which is kind of embarrassing. But we used his mathematical equations for, I don't know, about 400 years until a really smart guy by the name of Albert Einstein came along and said, as I look at Newton's calculations, I discovered that the speed of light, which, by the way, nothing in the universe can go faster than the speed of light. In fact, Einstein was so good with light, he actually won a Nobel Prize with his work, and it had something to do with light, but he had a problem. Newton's mathematical equations regarding gravity, there was a particular situation in which Newton's calculations predicted that gravity was faster than the speed of light. And so in this particular scenario, if the sun were to disappear, the Earth would change its orbit instantaneously, all right? And so the problem with that is that the gravity of the sun, which holds the Earth in orbit, would disappear instantaneously. And the Earth would leave, but the truth is that by the speed of light, in other words, a light particle takes 8 minutes to get from the sun to the Earth, which means that gravity actually traveled faster than the speed of light. And Einstein didn't like that. He thought that was a little goofy. So he wanted to try to figure out what was wrong with the Newtonian model. So he said, well, Newton never really explained how gravity worked, so maybe we could start there. Maybe there's something within how gravity works. And he took a little bit of time to figure it out, and he developed this theory of relativity. And Einstein's theory of relativity said, maybe space and time are connected. Maybe three-dimensional space and time are woven together like a fabric, and very massive objects like the sun put indentations into that space-time fabric. And so then if the sun were to disappear, it would cause like a ripple effect in this space-time fabric, which, by the way, took exactly the same amount of time to reach the Earth as the light did. And in this model that Einstein created, we saw that gravity could not travel faster than the speed of light. And well, since the sun hasn't disappeared, we don't really know. But since then, we have figured out that Einstein's calculations are true. And it's kind of like a unified theory or idea regarding gravity. Well, when it comes to gravity and roller coasters, luckily we don't have to go beyond, we don't have to know relativity to do that. And so if we just use Newton's model, which technically is connected to Einstein's, they're not different models, except Einstein's deals with bigger and smaller things. The way a roller coaster works is that we have the roller coaster at the top of the track, and gravity pulls on it. In fact, we call the acceleration due to gravity g, which is 9.8 meters per second. As it pulls down on the cart has the highest potential energy at the top of the hill. We'll explain that in a second. But as it pulls down on the cart, the cart starts to move, and so the potential energy gets converted to kinetic energy. And that's basically how a roller coaster works. So most roller coasters that you ride, they have some sort of device that pulls or pushes the cart up to the top, and as it comes down to the bottom, it changes into kinetic energy. So now, before I hit start, notice that I have my highest potential energy, which is the PE, and as I get close to the ground, that gets converted to kinetic energy. And so we'll do that again real quick. I'm going to set this to where the potential energy is here at this blue bar, and then I'm going to hit start. Now you would think if it all gets converted to kinetic energy, then when I get to the bottom of the hill, I'll have zero potential energy, and my kinetic energy should reach up to that light blue bar. The one thing I didn't mention is that the purple bar represents the mechanical energy. Now the mechanical energy is the sum of the potential energy and the kinetic energy. And notice that that purple bar is going down. Well, the reason the purple bar is going down is some of our energy is getting used up to overcome friction and air drag or air resistance. And that's how things work in the real world. So energy isn't necessarily conserved in the way that we would like to think here on Earth. But if it was possible and I could turn off friction, if I could turn off air resistance, then all of my potential energy would be converted into kinetic energy. And so if that were the case, if I could turn off the air resistance and the friction and the energy that's used by the roller coaster, then all of the potential energy would be converted. And so the potential energy plus the kinetic energy equals the mechanical energy. Right now I have the full potential energy and the full kinetic energy. So I'm going to turn off friction and air resistance, and notice that my mechanical energy doesn't change, which means that all of my potential energy gets converted to the kinetic energy. Unfortunately, in the real world, it's not how it works. So what mechanical engineers have to do when they design a roller coaster is they figure out what their potential energy is, which is really based on height and gravity, and then they need to make sure that the second hill is not too high, because if it is too high, then they may not have enough mechanical energy to make it over the second hill. So I'm going to slowly stop this, and so we lost a little bit of energy. And so let's see if it makes it over the hill. In other words, we may not have enough kinetic energy to push it over the hill. And let's see. It's close. It's very close. Let's see. I'm going to hit start. We have a little bit there. Maybe it's enough to get it over the hill. Nope. So that would not be a fun roller coaster ride. So what mechanical engineers do is they do this mathematically. They just don't build a roller coaster and adjust the height of the second hill. They make all these calculations. So by lowering that second hill, I should have enough energy to make it over the hill. And let's see, I stopped. Do I have enough? It looks like I do. Let's see. I do. And so what they do is, if you've ever ridden a roller coaster, every roller coaster or traditional roller coasters have the first hill is the highest, and then every hill after that is lower, and that's to offset the mechanical energy that's lost due to friction and drag, which is air friction. It's all lost to friction and heat. And so that continues on for the rest of the ride. So if this second hill is still too high, I need to readjust it. And so the first hill gives it the greatest potential energy, and that potential energy gets converted to kinetic, and then to potential, and so on and so forth. Okay, so how does the roll falling to a little bit? When you're on a roller coaster, you're not quite up as high as Felix is, but that's where the potential energy comes from. He had a potential energy that got converted to kinetic energy. On a roller coaster, it's on a much smaller scale. When the roller coaster is at the top of the first hill, gravity will pull on it, and as it pulls on the roller coaster, it changes position, which causes it to speed up, so it accelerates to a velocity. And that applies a force on the roller coaster, and that force can carry the roller coaster through for the entire ride. That can even carry it through what we call a loop-to-loop. Okay, so loop-to-loops on a roller coaster work on the principle of centripetal force, although sometimes people use the term centrifugal force, although centrifugal force is not a force, it's more of an effect. And centripetal force kind of keeps us in the cart, but it's actually Newton's first law of motion that keeps us in the cart as we go around the loop to loop. And basically your body wants to continue going in a straight line, and the loop actually redirects your path. And so I guess before we talk about that, let's try to understand what centripetal force really is. And centrifugal is more of an effect of centripetal force. So as we ride a roller coaster, what happens when we go through a loop-to-loop is basically our body wants to continue in a straight path, and the roller coaster is being forced by the track to go into a different direction. So as we ride through a loop-to-loop, we feel like we're being pushed up against the bottom of the track, and we call that centrifugal effect, but it's really an effect of Newton's first law. And so at the top of the loop here, our body wants to continue traveling the straight path. And this is because of Newton's first law, right? An object will remain in motion in a straight line unless another force acts upon it. But the track redirects our path, which makes us feel like we're being pushed down in our seat. This is an effect, not a force. So as we ride the roller coaster around the loop to loop, and I'm going to pause this here, we continue to want to go straight, and the track purposefully redirects our path, and it does it so fast that we don't have time to fall out of our seat. This effect is due to centrifugal effect. And so this occurs in circular motion, and really what I wanted to talk to you about was centripetal force. So uniform circular motion refers to the motion of any object that's traveling in a circular path. And this not only occurs in loop-to-loops, but it happens all over the roller coaster. In fact, that's one of the reasons why they're so much fun. So any roller coaster has circular paths, and so we're constantly changing direction. Therefore, we're changing velocity and changing acceleration and experiencing a bunch of forces on our body. And so you might say, well, what's so special about circular motion? Well, let's look at this Olympic hammer thrower. Now, he throws the ball, and we always think, well, the reason that he's throwing the ball is centrifugal effect, right? But really, that's just Newton's first law. But let's re-evaluate what's actually going on, the circular motion, and then I'd like to explain the difference between centrifugal effect and centripetal force. As he spins the ball, he is going around in a circle. Now, let's assume that the speed doesn't change. Well, velocity is a vector, but its direction is constantly changing, and it's always changing tangent to the path of the circle. So the velocity is changing its direction, but not so much its magnitude. And when the velocity changes, it's undergoing acceleration. Because remember, acceleration is a change in velocity. Well, because of vector mathematics, we can only assume that the acceleration is pointing towards the center of the circle. So we call that centripetal acceleration. And we can calculate that by the velocity squared over the radius of the circle. The direction of the acceleration is constantly changing, always pointing to the center of the circle, which is always causing the ball to stay on the circular path. That's why when he lets go, once he lets go, it just wants to travel in a straight path. If he didn't let go, it would just continue around in a circle forever. So what causes the acceleration? Well, if we look at this racing car, there's some things that kind of keep it in its circular path. But if centrifugal effect were true, then the car would just fly off the edge as it came around the corner. And it's true, there's lots of forces that work on the car, and we angle as we come into a turn on a racetrack. And I suppose if we were supposed to draw some sort of free body diagram, there's the effect of gravity and the normal force. But there's all kinds of forces, and they, I guess the main one that I want to talk about is centripetal force. Because it's the centripetal force, or the force that forces the car towards the center of the circle, and that's the same direction as the acceleration because of Newton's law, right? And so according to Newton, he said that force was equal to the mass times the acceleration, but in circular motion, the acceleration is always changing and pointing towards the center of the circle. So the direction of the force is the same as the direction of the acceleration. This is what we call centripetal force. So I hope that you enjoyed learning about the physics that are used by engineers to build roller coasters. And if I were to summarize, I'd say that when we change our direction, we change velocity and we cause ourselves to accelerate. And whenever we accelerate a mass, we apply a force to it. And if we do that enough, quick enough, our body experiences all kinds of fun things. So the next time you're at a theme park, enjoy yourself and have fun.